Alright, in the last video we became familiar with this equation where this was the shear stress, this term was the strain rate, and this term was the viscosity. What this implies is if we made a plot and we put down here the strain rate, and which would be this term, and up here we put the stress, we should get some sort of straight line like this. And the slope of these straight lines should be nothing more than the term, the viscosity term that goes right in here. But this doesn't always occur. And let's look at some cases and discuss some reasons why this does not occur. Let's look at this term again, or this plot again, and just put this term in here as reference. There are times in which you could have a nonlinear behavior, something that would occur and look like this. This is what's called shear thickening. Then you could get something that looks like this, shear thinning. But you could also get something that has a simple yield stress, something that you could stress it and it won't move, and then as you, here let me make it a little bit more. So as you stress it and move up this curve, and you're moving up to the point where suddenly it begins to flow, and at that point it does behave like it might behave where there was a constant slope, but it might not necessarily. That's sometimes called a Bingham plastic. Okay, now typical cases of Bingham plastics would be toothpaste. You open that toothpaste, turn it upside down, nothing happens. Then you start squeezing the tube, and out comes toothpaste. Ketchup. Turn it upside down, you've got to squeeze it to have it come out of the bottle. So these are cases in which you've got to come up with a effective yield stress, or in order to get the thing to start flowing. So you stress it and then it begins to flow. That's the yield right here, the yield stress. These occur generally out of becoming some polymeric. But the story doesn't end here. Let me give you a typical case. Or let's confine ourselves, or let's not do this, but let's say that this course actually does confine us to these type of fluids. These are called Newtonian fluids, and for the most part, the most common fluids on Earth are air and water. A majority of everything you come across and that you'll deal with is air and water, unless you go work for a petroleum industry or something like that, and you'll deal with things a little bit different. We'll talk about that in a second. If you look at water, for example, the molecular makeup looks like that. It's just H2O. You could have another H2O particle sitting over here, but they could move independently of each other. If you plotted their path for, say, this particle may start here, or this molecule may start here and move around like this, and this one may start over here and move around like that. if they, at a certain time T1, say this was the location of these two molecules, they're completely independent. They've moved away from each other. They're not tied to each other. Nothing of the sort. Same thing with air, except air has nitrogen, oxygen, things like that, so it has multiple molecules, but they are not tied together. They're just simply molecules. You could have O2, O3 out there, nitrogen, things like that. They behave in this same manner. As opposed to that, let's look at something like this. Let's say we look at a long chain polymer. Something that has a bunch of carbons, like a whole pile of carbons, all connected with a bond through here. I'm not doing a very good job. They could have things attached to the sides, out to the ends. So it would look like this. Now, if you looked at this, and this particle, this atom ended up over here, and this one ended up over here, it would stretch this. Now, if you stretched it hard enough, it would pop one of the bonds possibly, but in effect, a polymer might have another one of these attached, in which you could think of these as being a large set of rubber bands. So it's basically a rubber band fluid, you could say. Now, how does that change things? Couple of things. One, this changes completely. It's not Newtonian at all. Second thing that happens is this. Let's say you took two beakers and you filled one with water and you filled one with the long chain polymer. I'll say LC long chain polymer. Then you took just a regular drill and you put a pencil in that drill. I'm not going to do a good job of drawing the drill, but say here's your drill, and it has a handle over here and it has a trigger. So this pencil is rounded. If you look at it, its cross section looks like that. Then you go in and you essentially drop that drill in here and you dropped it in here. So you had essentially the drill bit sitting in here, which is going to start spinning. You have a drill bit in here that starts spinning as well. Now if you look over here, what happens to the water, something logically happens. So the water starts spinning as well, and pretty soon what you have is you have the fluid behaves much like this. It's slung to the side, and as it moves, the particle here moves around and out into here. The centrifugal forces and the rotation basically moves the fluid interface to look like this. Over here, something drastically different happens, and the exact profile I'm probably not going to be able to do, but it does something like this. The question is why? And the answer to that is just a simple explanation. If you were sitting up here looking down, this little green man here, what you would see over here would be this. Okay, the green man sees this over here. What he sees is a large number of rubber bands, essentially, because it's a long chain polymer, all dispersed throughout this fluid everywhere. As this thing starts to turn, let's take a look at just one of these rubber bands. Let's say the rubber band just happens to be sitting like this. There's got to be one rubber band in all this that does that. As it turns, this end of the long chain polymer will be drug around the spindle. This one will be slowly drug in that way, but as this one is wrapping around this, it tightens up, and what happens is it's dragging all the particles that are sitting, or not the particles, but the atoms that are sitting way out here towards this, because even if they're not like this in perfect formation. Say you have a long chain polymer like this one will start pulling and it'll start stretching this part and wrapping it around tighter and tighter. So essentially what you have is rubber bands that are wrapped tightly around this. You see this when you take eggs and you put them in there with the an egg beater, and you spin around to mix for some type of say cake you're making or something, or icing or whatever you happen to be making. You can pull the beaters out, and of course the beaters are not shaped like a pencil, they're shaped like this, but you may have egg white all over this, sort of hanging onto this. This would never occur if you put an egg beater in water. You put an egg beater in water and it spins around. Basically you take the egg beater out, and what happens is the water just falls right off of it. So the fact of the matter is, long chain polymers behave much different than just simple dispersions of molecules. The long chain polymers are connected to each other. They behave different. They essentially behave somewhat like a solid and somewhat like a fluid as well. There's some properties of them. The long chain polymer parts are solid-like. The fact that they flow amongst each other is a fluid. Over here there's nothing but fluid. There's no solid behavior, there's no memory, there's nothing. Long chain polymers are also used in the petroleum industry a lot, and as a result their behaviors can be very helpful in moving petroleum products around.